Hello everyone. My name is Saladin Laidoudi from the EBISC laboratory at the University of Paris-Saclay and the ISME Research Lab. And this talk will present our paper, Dual-Focus Multiscale Attention for Object Detection in Mixed Reality, leveraging customizable synthetic datasets. So here's the plan for these next 12 minutes I hope. First, a short introduction, why detection is the entry point for any MR interaction system. Second, a literature review, a short literature review on marker and markerless recognition systems. Then our contributions, which are two main contributions, the hybrid background synthetic datasets pipeline and our DFMA module. And lastly, we will conclude this presentation. So, mixed reality overlays 3D content on the real world, so detection is the entry point to every interaction. In real deployments, on mobile or wearables, we face low latency, tight power, and tiny memory budgets. So, why MR detection is hard? First of all, general purpose detectors are trained basically on benchmarks that are such as the COCO datasets, such as YOLO or DTR, which are not really MR aware, where we have moving cameras, depths, occlusions, real-time constraints, etc. So this on-device, these tiny models are required to detect in real time, and that's a huge problem in MR, for example. And our main goal here is to create a robust and accurate on-device detection model in uncontrollable or uncontrolled MR environments without losing real-time performances. And we have two main problematics. First of all, we must choose a scenario that showcases a real-world MR problem application, and we need to develop this robust real-time object detection model. For the scenario, we chose a classroom astronomy scenario where we need to recognize planets in a classroom and overlay interactive 3D content in real time. It is relevant because of indoor environments, lighting, moving camera, occlusions, clutters. Then these constraints are unavoidable, and the objects are really low textured and look alike. And there is also the scarcity of data or labeled data in MR or in object detection in general. And devices as well have this tight power memory. And this setup mirrors other MR domains such as industrial parts or medical models. So recognition in mixed reality comes in two families. For example, here on the left, we have marker-based methods where we place visual markers such as QR code, barcodes, or printed image targets, so the system locks on reliably. They're robust and simple, but they break immersion and need setup and maintenance. On the right, we have markerless methods. With natural features, we detect edges, interest points, think of SURF or SURF algorithms. We track optical flow or cues, depth imaging to localize without markers, or maybe with sensor-based cues such as inertial or acoustic, magnetic, or a GPS. We stabilize and complement the vision models. And our work sits here. We push markerless vision-based detection to be robust enough for real classrooms without needing any markers. So in a nutshell, here's the big picture of object detection over the last 2 decades. We start with the classic pipelines such as Viola-Jones detector, the histogram of oriented gradients, or the HOG, the DPM, and with the emergence of the first deep learning model, AlexNet, in 2012. And we have the two-stage family that begins with RCNN, fast and faster RCNN from 2014 to 2016 with strong accuracy, thanks to region proposals. And in parallel, we have one-stage detectors, which in themselves can be also classified into anchor-based and anchor-free detectors. And during the state-of-the-art study, this table highlights the speed accuracy trade-offs. We have two-stage, which are accurate at the time, one stage, which are more real-time or more faster, if we can say so. And lastly, we have transformer-based models that add global context to keep improving on the onward to real time. And our works aims for the sweet spots, strong accuracy and compute while remaining truly on device. So our main two contribution, first is a customizable synthetic datasets pipeline with hybrid backgrounds tuned for MR. Second is the DFMA or dual focus multi-scale attention module, which is a plug and play module integrated in a YOLO style backbone plus an FPN to boost accuracy at nanoscale. Together, the dataset pipeline and the DFMA deliver high MAP with minimal compute and real deployment in Unity using the Centis framework. Our datasets start from Blender renders of planets. For each 3D model, we render 4 cameras around the 3D model at 20 angles. So we have 80 views per model to diversify pose. We export the foregrounds with alpha for clean mask and compositing. We then compose with hybrid backgrounds, approximately 60% synthetic space, which are basically gradients and artificial stars, and 40% real backgrounds from the Google Open Images datasets. And objects are placed with random position and basically with all the data augmentation techniques, different brightness, random places, etc. And annotations are in the YOLO format as well. So first of all, we compared the Open Images only backgrounds against our hybrid strategy, keeping everything else fixed at 20K images for training and 5K images for validation. The MAP at .5 and .95 jumps from a whopping 77% to 98% with the hybrid backgrounds. And the key takeaway here is that simulating space-like context alongside real clutter improves robustness for low textured and lookalikes targets, and it better reflects MR deployment scenarios or conditions. As for the detection model, it is a lightweight YOLO style model with a 5 stages background, P1 to P5. These stages are composed of the CSP layers that extract multi-scale features, and at the end is a custom SPP or spatial permit pooling layer that adds global context at the top. And we have the bidirectional FPN neck, a top to down and bottom up fusion that aligns the 3 stages P3, P4, and P5, and we insert our module, or the DFMA module, at key tabs to refine features. We insert them after the first and the second and the third CSP layers. As for the detection head, it's a classic decoupled detection head, a branch for bounding box regression with a complete intersection over union and a DFL loss. And for classification, it's a simple classification head with a binary cross entropy loss. As for the DFMA, which stands for Dual Focus Multiscale Attention, it has 2 paths on the same feature map. First, the multiscale spatial attention looks at where the object is by aggregating channels, averaging and maxing, and applying depth-wise convolutions at 3 different kernels, 3x3, 5x5, and 7x7, combined via learnable weights. This brightens true objects regions and suppresses clutter. Second, the channel attention, or the dual pooling channel attention, that decides which channels matter most using both global average and global max. Pooling plus a lightweight bottleneck and cross-stage reinforcement gates, which we call here gamma. Finally, a group normalization layer and the adaptive residual scaling beta to stabilize training. Here are the training hyperparameters. For completeness here, the training details. We train at 640 by 640 with a batch size of 32 for 600 epochs on a RTX 4090. The optimizer is a SGD with a momentum. We use linear RR scheduled with a warm-up, and we enable AMP mixed precision. As for the benchmark, we benchmarked our model against other models on the MS COCO validation datasets. Our DFMA achieves MAP at around 48.3. So here, compared to other models, we offer the best accuracy per flop or per flops among nanoscale options, preserving on-device feasibility. And to compare our DFMA or our attention module, plug-and-play module, against other attention modules such as the SA, ECA, or CBAM, or CA, and EMA, we can say that DFMA is the best, giving a whopping 48.3 MAP at different intersection over union thresholds, while adding only 0.2 million parameters, which is approximately 6%, and 0.2 G-flops, which is approximately 3% to the baseline, which is a superior accuracy per cost trade-off for low textured lookalike objects. And here we deploy on device in Unity using sentence inference framework. The inputs are the live camera, texture to 2D, a DFMA on NX model, and the 3D assets library. We pre-process on Unity and infer using sentence, which returns classes and scores. We post-process using thresholds and non-maximum suppression. We convert bounding boxes coordinates to screen word space coordinates and apply light temporal smoothing. Then we spawn and place the matching 3D models. At the center of the bounding box, we do some scaling, and the mixing shader blends real camera and virtual render for coherent overlays. And the result is real-time MR views with stable augmentations. In real-world tests, the nano model remains robust enough. For on-device processing, you can see stable detections and smooth augmentations, including differentiating Mars from the sun, for example. That's something that other models could not do because they look alike a lot. Mars is red, the sun, it's also red, and they're both round. This validates that the accuracy gains translate to user visible MR stability. So to conclude, we managed to create a hybrid data sets pipeline and a DFMA plug-and-play attention model that delivers higher MAP. In AMA demos, it reduces lookalike confusions and yields more stable boxes for real-time overlays, and the data pipeline is reproducible and transferable to other MR scenarios beyond astronomy, of course. And at least we acknowledge, of course, our limitations. There is always a sim-to-real gap under unseen lighting, motion blur, or materials still cause error. We have a narrow class set, and of course, we did not do it on-device profiling because we didn't have the time to, but that would be great if we can manage to do it in the coming months. For future work, we want to do some domain adaptation, maybe expand on the data, explore more the on-device optimization, maybe int8 or int8 quantization or other MR-specific robustness, maybe a multitask head, doing other tasks other than object detection, and that's it. Sorry. Some references, and thank you for your attention.
Perfect. Thank you for that presentation. Do we have some questions by the audience? Someone? Then I may start. You have shown that the application or the approach is included into Unity, right?
Yeah.
And you also have shown in the previous approaches the timings. How long does it take to detect a marker, right? To detect the image. In comparison to these previous approaches, how more faster is your approach?
Okay, maybe.
In terms of milliseconds, for example.
Yeah, in terms of speed, the model we can translate how fast the model is by looking at the flops or the floating points operating per second. So, as I said, we offer the best accuracy per flop. So it's a compromise. For example, here we can see that for example, the efficient depth is just 2.5 G-flops, but it gives an MAP of 31. Compared to our model, it's about 48% at only $7.
And what kind of hardware do we have tested these numbers?
We tested on three different hardware. We tested on a desktop with desktop with 2070 RTX 2070. It worked great. We tested on the tablet S7 FE. It was I can say it was on real time, and we tested also, for example, the last images from MetaQuest 3.
Okay. Yeah. That would be my next question, but yeah, okay. So I also tested on VR HMDs or XR HMDs. Okay.
And on MetaQuest, I can say it was seamless. I think the hardware is not there yet to run a real-time experience.
Okay.
But it worked.
Okay. Oh, now we have a question. Yeah.
Yeah. Quick question. Thank you for the talk. Very interesting work.
Thank you.
So for YOLO, I forget which version you're using, but do you make use of the cropping parameter, the option that you can turn on that takes your images or your source images, crops them onto other backgrounds for robustness, or do you even need to use that?
You're talking about the in the training pipeline on YOLO?
Yeah.
Because in fact we created everything from scratch, so I didn't know didn't use the YOLO pipeline training.
Okay.
Yeah.
Cool. Thanks.
Thanks.
Okay. Do we have more questions? No? That's actually quite okay because we are a little bit behind the time. So thank you again for the presentation.
Thank you.
Yeah, good afternoon, everyone. I'm Cheon Lee from Samsung Electronics. I'm really excited to present our work, Ego Blur, blurry egocentric XR dataset for robust fast hand pose estimation. I worked on this project together with my Project Mohan team members from Korea and India. So let me start with a bit of motivation. Hands are the main interface for interacting with virtual content. Thanks to vision-based hand pose estimation models, we can track hand motions really precisely. User can pinch, select, punch, and even play virtual instruments. Examples like air guitar and Move Fast from MetaQuest. These are the typical dynamic hand gestures. So having reliable hand tracking is really important for creating realistic and immersive XR experiences. Large-scale, high-quality datasets, such as Interhand and Umtrack, have contributed a lot to hand pose estimation. However, most of them were collected in slow motions or very controlled settings, so they don't really capture all the fast, natural hand movements, especially those with real-world motion blur that happens during quick hand dynamics. That's exactly what inspired our work. When we use XR devices such as MetaQuest and our prototype Android XR device, we often make quick hand gestures without realizing it. Of course, most of the time it works fine, but under slightly different lighting conditions like low light or outdoor sunlight, you might notice that hand tracking struggling to keep up with fast movements. Sometimes it stutters or lags behind. That's because of motion blur in the image. Blur significantly degrades tracking quality in XR devices. Generally, XR devices perform well under normal lighting conditions. As you can see in the video, they achieve clear images by using short exposure, high exposure gain, and high frame rates. However, these camera settings consume much more power, which is critical for mobile XR headsets. Lowering the frame rate or increasing exposure can save power, but it inevitably causes motion blur. So there's always a trade-off between image clarity and power efficiency. Therefore, developing a blur-robust hand tracking model is essential for practical and energy-efficient XR systems. So our main contributions consist of two parts. First, we present Ego Blur, a new egocentric dataset of blurry hand images captured directly from our prototype XR device. And second, we propose Ego Blur Net. It's a novel method trained on our Ego Blur dataset for 3D hand key point estimation from blurry inputs. It is robust to motion blur in realistic XR conditions, leveraging knowledge distillation techniques. Before diving into our main method, let's briefly look at related work. There have been some studies dealing with motion blur, for example, Blur Hand and EBH. But Blur Hand uses synthetic blur, so it's quite far from realistic blur in real-world settings. EBH, on the other hand, deals with real blur, but it's not captured from an egocentric point of view. So there's a clear need for a dataset that captures distorted monochrome images from real XR headsets. And that's exactly what our dataset provides. So to build this dataset, we created our own data capture setup for collecting eagle blur. This setup consists of two main stages, synchronization stage and a key point generation stage. Now let's take a closer look at each stage. First, in the synchronization stage, we capture hand motions using the data capture rig shown on the right. It consists of a prototype XR headset surrounded by 70 high-speed smartphone cameras, each recording at 120 frames per second. Since these devices come from different domains, we trigger the capture over Wi-Fi and then align them using a light-based synchronization method. Specifically, we flash a light once, and each camera detects the frame where the brightness suddenly increases. That frame serves as the timing reference for synchronization. Once the frames are synchronized, we first perform call map calibration on the synchronized images. Next, we run Ransack-based optimization to generate 3D key points. Specifically, we start from 2D key points predicted by pre-trained SODA model on the high-speed camera views, remove outlier views with large reprojection errors, and iteratively refine the 3D key points. Finally, we reproject the optimized 3D key points onto the HMD's blurred frames based on synchronized timestamps. This way, we can obtain accurate 2D and 3D ground truth levels, even under severe motion blur. Each blurred frames contains initial, middle, and final key points, capturing the hand's motion trajectory within a single image. Using this pipeline, we built two subsets of the Eagle Blur dataset. On the left, you can see Eagle Blur SB, our synthetic blur subset. The synthetic blur was generated by applying weighted averaging over consecutive sharp frames. This gives us sharp blur frame pairs, which are used to supervise the model that I will introduce later. On the right is Eagle Blur Rear, our rear blur subset. Here we recorded a wide variety of natural hand movements like pinching, grabbing, and counting to represent realistic hand motions in XR environments. Altogether, our dataset contains about 100,000 egocentric hand images covering diverse and dynamic hand movements. Using the Eagle Blur dataset we just introduced, we trained our model, Eagle Blur Net. It's built on a cascaded pyramid network with a ResNet 50 backbone. And it predicts 3D key points. The training process is quite straightforward. It consists of 3 stages. First, we pre-train the sharp post estimator and the blurry post estimator independently using sharp and synthetic blur images. Second, we distill rich hand pose features from the sharp teacher to the blurry student. That is, from the sharp pose estimator to the blurry pose estimator for each sharp blur pair. Finally, we fine-tune the student on the real-world blurred dataset. This step bridges the domain gap between synthetic blur and real motion blur, making the model more robust under realistic XR conditions. Here we can see the effectiveness of Eagle Blur dataset under blurred conditions. We compared 3 methods, blur hands, which is trained on blurry images, and 2 state-of-the-art models, A2J and key point transformer, both of which were trained on normal, sharp images. We evaluated them on 3 datasets, the synthetic blur track dataset, which is also egocentric view, the blur hand dataset consisting of synthetically blurred hand images, and our ego blur dataset. The results show that models trained on normal images struggle to estimate 3D key points accurately under blurred conditions. Blur hand performs slightly better, but still fails to generalize well to track and ego blur, highlighting the importance of egocentric data and blur-aware training. We also observed the effectiveness of ego blur net against state-of-the-art models, A2J and key point transformer, on our dataset for a fair comparison. This shows that while retraining helped slightly, but ego blur net still outperformed all of them by a clear margin. On synthetic blur, it was about 5 times better, and on real blur, it was about 3 times better. As you can see on the left, our model keeps accurate key points even under strong motion blur, while others completely lose track. In the ablation study, we first analyzed how our training strategies affect the performance of ego blur net. It turns out that without knowledge distillation and real blur fine-tuning, the accuracy drops significantly. However, when we combine both strategies, we achieve the best overall results. So both steps are crucial for making the model robust to real-world motion blur. We also examined the system efficiency, specifically how the frame rate and exposure time affect power consumption. The numbers shown here indicate the difference from the default configuration, so higher values mean greater improvements in each performance measure. As shown in this table, lower frame rates and longer exposure times can significantly reduce power consumption and CPU load. This suggests that blur-robust hand tracking models like ours can directly help build more energy-efficient XR systems. For the application, EagleBlow.net is seamlessly integrated into our XR device. It's integrated into the XR solution layer, where it processes camera and IMU data and outputs 3D hand key points to the OpenXR runtime in real time. Our EagleBlur dataset, which includes 3D key points, can also be extended to other modalities, such as hand mesh and segmentation mask. To conclude, we introduced EagleBlur, a new first-ever egocentric hand dataset captures real-world blurred images from a prototype XR device, and EagleBlur.net, a hand pose estimation model that have robustness under motion blur. Together, they enable accurate and power-efficient hand tracking for real-world XR systems. So thank you for your attention.
Do we have questions? Yeah, there's one question.
Thanks for your great talk. May I ask, how do you generate the ground truth annotation for the blurry images? If the images is blurred, you don't know the ground truth pose of the hand.
Oh, yes. So in this data capture setup, there's 70 high-speed smartphone cameras surrounded by MTMD device. So these smartphone cameras recording at 120 FPS. So these cameras can capture fast movements of hand.
Okay.
And we can generate key points from these views and project to our XR device view so that we can get accurate hand key points.
Okay, I see.
Yes.
My second question is, what about the inference speed of your method? Can it run on real time? The inference hand pose estimation speed.
Oh, sorry. Can you repeat?
The inference speed of
Mhm.
your hand pose estimation model.
Ah, yes. Inference speed is, I mentioned in the paper. I I I can't remember the exact number, but it's about 10 to 12 milliseconds.
Okay. So what about the comparison of your method with previous method that run on clear images? Let's say maybe input a clear image, no blurry, and compare your method with previous methods.
Oh, can you repeat?
Uh,
Yes.
if I input a clear image, the image is not blurry, and compare your method with previous hand pose estimation methods. What about your method, the performance?
Comparing with clear images.
Yeah, clear image.
We haven't explored that part. We didn't compare with clear images. We only tested with blurry images. So
Okay,
yes.
thank you very much.
Thank you.
Perfect. So thank you again for this very nice presentation.
Can't tell you how good it is to be back on stage and to see you all, friends and familiar faces. And this has already been a really cool session, so thank you for being here. All right, I also would like to talk about object detection. And just a show of hands, how many of you use YOLO or SSD or a similar architecture in some of your research? Couple, okay, maybe 15, 20%, not too bad. Okay, so I'm going to talk about YOLO, but first let me talk about what we're trying to do here. So in trying to detect objects in the real world, in augmented reality, mixed reality, I think a lot of you have seen images like this on the left-hand side, right? You can detect objects using YOLO, for example, people, plants, the 80 or so objects in the COCO data set. And ideally what we want is when we put on a head-mounted display or another augmented reality device, we want to be able to label those objects in real time accurately so that we can see information about them. Right, if you're, let's say you're training your mechanic, for example, and you want to see information about an engine, you should be able to see, to put on a device, see the parts of the engine, and display that information in real time without any problem. So that's all good and nice. And some of you, so the image on the right here, you may have seen this video recently. There's a lot of work being done. Some of the work in this room, had a couple other talks of how to get these images, how to display them in real time, and how to make sure that those images stay where they are, for example, right? So YOLO is sort of notorious for missing frames, and if you just use YOLO in sort of its raw form, you get missed frames, some of the objects disappear from time to time. We don't want that, right? So what we want to do is build a modular framework, something that is going to let us be more flexible than YOLO itself, and conquer some of these problems. So one of the big problems with data sets like YOLO is they're very expensive, right? You have lots and lots of images. You have to train on those images, and it takes a long time to train YOLO, hours, sometimes days, depending on your data set, right? And they're very inflexible. If you want to add your own object to a data set, you have to retrain, and that can be on the order of hours. It's not intuitive how to do that. And a lot of times it's difficult to add custom objects. Sometimes VLMs, right? There was a talk earlier today about using vision language models to return objects. They can return generic items a lot of times, but they can't return your personal items, right? If you want to train on something in particular, let's say you're learning a language and you want to get a translation for an object that's unique to you, you can't really do that with frameworks today. So our goal is to overcome that. There's been some recent work, again, some of the work that's been in this room today on how do we get YOLO or other frameworks onto mobile devices, how do we do these detections in real time. That's ever increasing. Another thing I want to talk about just briefly is incremental learning. So incremental learning, also it's called active learning, sometimes transfer learning, is a field in which we ask the question, how do we when we get a new object class, we want to add a new object class to a data set, how do we do that without having to retrain from scratch? So I'm going to show you how we're going to use mixed reality, labeling of mixed reality objects, and incremental learning to do just that. So very simply, what we have built is a one-shot method for labeling an unclassified object, some custom object that is unique to you. So in the upper left-hand video here, you'll see a little robot, which is kind of a unique robot it's not part of any data set, right? And we want to label that such that, one, it's immediately usable, and two, if we move it across the room, it's going to be redetected and still usable despite that move, right? So the first step in our framework is to label it. And not just label it, not just select it, but actually label the voxels. So you'll see a little 3D box here that we're labeling around it. Our framework is going to, in the background, retrain based on that object, and I'll talk a little bit about how we gather that data here in a minute, but it's going to retrain on that object. We can do it on multiple objects, and almost instantaneously, we can redisplay them in the real world with very good stability and fairly good enough accuracy to be practically usable based from what you can see down here on this video on the bottom. And this is just a language learning app where we display the source word and its translation in Japanese. So, how this works, we have really three main steps and then sort of a demonstration. But the first is labeling the voxels, and we provide two methods to do that. We kind of make them intuitive for this particular mixed reality workflow. Secondly, the real magic here is how we create the data set based on those voxels, those selected voxels. Third, how we use incremental learning, so how we use the newly generated data set, automatically upload to the server, and automatically retrain in the background so that perceptually the user doesn't even realize the retraining is going on. And then lastly, how we demonstrate that. So first off, the annotation process itself. The left-hand image here, we call this multi-point bounding. So if you have an object that's nearby and you have a controller, you just label, basically you can stick the controller next to the object and use a raycast to select 4 points that create a rectangular solid or cubic bounding box around the object. Second way, so we use that, but we found that when you want to label something far, so like in the very back of the room, you can't exactly stick the controller in it. So we created a second method where you take two controllers and you sort of use them like the intersection of the rays. That selects the center of an object far away, and then you use those rays to scale the object, and then you can rotate them to select even large objects or far away objects. So we have these two methods that basically allow for easy selecting of the voxels of any object, whether that's nearby or far away. The second part of that, and this is where the really important part. So once you've labeled the object, we start collecting, so this is a source image in the lower left here. We do the 3D to 2D bound computation. So from those voxels, we get the 2D image. That's labeled, and that's sent automatically to a REST API where eventually it will be retrained. So again, the label image, you get the voxels. We compute, based on this 3D bounding box, we can compute a 2D bounding box. That sends a 2D image back to the data set, back to our YOLO integrated framework, and that retrains in the background. The awesome thing about this is it eliminates manual labeling for new objects. So if you have a custom object, right, in not the old days, but generally you have to manually label it, right? You take a bunch of different pictures, you have to label them, that's one object, et cetera. There's some automated ways for that, but this really streamlines that process. Secondly, incremental learning. So this is a really important part in terms of how we make the training perceptually, or almost imperceptible to the user. So first off, once we actually select the object, that label based on we're using the MetaQuest 3 for this, by the way. Based on the MetaQuest 3's internal positioning, we leave the label as is, just as an AR label, so that the user can immediately use it. In the background, we start this process called active or incremental learning. And what that does is, so for the YOLO framework, there's a bunch of layers, right? And then the head, which has the last layers. We freeze the first 23 layers of the YOLO dataset and retrain the head. So the head gets copies of the new object, the unclassified object, and several exemplars from the old data set. And this works extremely well in terms of giving good accuracy for the new object while retaining accuracy of old items. Secondly, this isn't extremely scalable in terms of we can't do thousands of objects this way. However, we do have a model selector. So if you have multiple models, let's say you have one room which is your garage, one room which is your office, and you have different sets of items for each, you can select between models that were trained in different environments, allowing for scalability. Okay, and the training, so retraining the head using incremental learning in this way. On the left-hand side, this is what happens if you retrain from scratch, right? If you need to retrain YOLO using a new image data set, it takes something between 50 to 90 epochs on the order of several hours. And I think we're using an RTX 3080 to do this. With this new framework, with incremental retraining, we go from about 3 to 20 epochs. And in general, this only takes about 20 to 30 minutes, well, 30 minutes max, sometimes less than 20 minutes, to reach MAPs of over 50% for almost all of the new object classes, while retaining fairly good MAPs for the old object classes. If you do this indefinitely, eventually the old object classes sort of fade out, but for the new object classes, the ones that are really relevant to your use case, we retain accuracy and they're immediately usable. And so this is the final product, right? So on the right-hand side here, again, you saw this video at the beginning, but these were all labeled using this process. Again, it's one shot as the end user. You just create those voxels, and immediately any object that you label, whether that's robot, scissors, book, etc., is immediately usable. You can immediately display information about it, and we can add large language model responses or direct translations if you're learning a language, for example, or instructions if you're a mechanic. And lastly, so another thing that's going on behind the scenes here, there's another paper we have on object tracking and object permanence. So how we use multiple frames and multiple recognitions over time to increase robustness of the display. The stability you see here is because we're aggregating multiple frames over time and using the internal tracking system of the MetaQuest 3 to establish permanence. So even if we have MAPs like accuracy of 50% roughly, we can still get this type of stability and this type of recognition accuracy. So next stops for us, and we've already started testing on some of these industries: aviation, manufacturing, automotive. We want to take this for training, for education, and into the industry space. And we would love to commercialize this. So if you have any business contacts or companies that might like to use it, please do let us know. So that's it. I would love to take any questions. And also, this is primarily the work of Ali Reza Tahiri-Tajar, one of my PhD students. So he deserves most of the credit for this. So thank you.
Any questions? There's one.
Hi, thanks for the talk. Very interested work. Congratulations. I think you addressed one of the biggest problems of training models, which is annotating. It's a big burden, and then you just presented something that will help to alleviate this burden. So thanks for your work. And about the automatic annotation process, do you have any kind of similarity measure to decide, this image, I already took some samples from that angle, so why not add this to the new training model and stuff?
Yeah,
Thanks.
so right now I believe we're using angular constraints. So the angle or the 6 degree of freedom position of the display has to have changed significantly. I don't know what the exact threshold is, but it won't retake images if they're just in the same spot, essentially. So these just have to move around a little bit. Typically, you're moving at least a little bit when you're taking images. But we also, the question I asked before, I don't know if you're here, about using the crop function of YOLO. Even if we do have very similar images, we use that crop function, and we still get pretty good recognition, whether we're moving to like a carpeted area, a different desk. Yeah.
Thanks. Very interesting.
I think.
Okay, perfect. Because of time, I would like to. Yeah, but is it a brief question? Then, okay. Maybe also afterwards. Yeah. Okay, perfect.
Thank you.
So thank you again for the very nice presentation.
Hello everyone, I'm Li Zhizhao from Beihang University. Our work is GSHOI denoiser. Denoising Gaussian hand object, denoising Our work is GSHOI denoiser, denoising Gaussian hand object interaction rendering together with Xuequan Lu, Binghu, Jianwu, Ke Wei, and Lili Wang. The authors are from Beihang University, the University of Western Australia, and Moscow Polytechnic University. So in this paper, we define a new task called Gaussian hand object interaction rendering denoising. The input consists of pre-trained hands and object Gaussians, along with a noisy hand pose, which means the hand fingers may penetrate with the virtual object or cause an unstable grasp. The task output should be the rendering images of the denoised hand-object interaction, which means we expect to correct the hand pose so that the 5 fingers contact the object surface correctly. The demo video shows our task in mixed reality. The initial noisy hand pose caused the thumb to penetrate into the apple. With our method, we denoise the hand pose to grasp the apple correctly. There are related works that explore mesh-based hand-object interaction denoising. Zhou et al. Pioneered the hand pose denoising method. Liu et al. Proposed using a diffusion generation model for post-denoising. On the other hand, Zhao et al. Proposed using 3D Gaussian splatting to render an animate hand in real time. Pokhariya et al. Rendered hand-object interaction using Gaussian splatting, but these methods have a condition. They are given the ground truth hand pose. In general, mesh-based hand-object interaction denoising method can handle the hand-object relationship representation and the hand pose denoising, but cannot render photorealistic appearance. And the Gaussian-based hand-object interaction rendering method can render photorealistic appearances, but require a clear hand pose and cannot perceive the hand-object interaction. Therefore, a straightforward intuition is, can we directly use mesh-based denoising method for Gaussian splatting? For example, we can treat the Gaussians as mesh vertices. The answer is yes, but there is a challenge we have to carefully consider. To represent the hand-object interaction, we need to sample points on the object surface. The mesh vertices lie accurately on the surface, but Gaussians are different from meshes. The right figure shows our visualization results of the object Gaussians. The colored spheres denote each Gaussian, and the gray contour denotes the ground truth object surface. We can see that the Gaussians are coarsely distributed around the underlying ground truth surface. So the challenge is, how do we model the accurate spatial relations between the hand and the coarse object Gaussians? In this paper, we propose a pipeline contribution and 2 technical contributions to solve the above challenge. Firstly, we propose the first 3D Gaussian hand-object interaction rendering denoising framework. Second, we propose a novel joint-to-Gaussian surface representation for capturing accurate hand-object relation. Third, we propose a novel geometry-aware depenetration method. In detail, our first step is to reconstruct the object Gaussians and hand Gaussians from multi-view images. Then, given a noisy hand pose, we animate the canonical hand Gaussians to obtain the initial noisy hand-object interaction Gaussians. The second step is to construct our proposed joint-to-Gaussian surface representation to model the accurate spatial relation between the hand joints and the object Gaussians. In detail, we first randomly select some object Gaussians near the hand skeleton as anchors, as depicted by the red discs. We then attach virtual cameras to each hand skeleton joints and set the cameras to look at each object anchor. Now we can render depth maps using these virtual cameras by Gaussian splatting rendering. And with the non-camera pose, we can unproject the 2D depth maps to the 3D points to obtain the underlying surface simple points as visualized by the blue spheres. We can see that although the position of the object Gaussians are coarse, our simple points shown as the blue spheres lie accurately on the object ground truth surface. Now we are able to construct the spatial representation by connecting each hand skeleton joint with each object simple points. Our third step is to denoise the constructed noisy spatial relationship using a diffusion model. Given the hand Gaussians, we first regress the skeleton joints of the hand. Then we train a diffusion model that takes the noisy representation as input and output the denoised clean representation. Since the object simple points are static, we can easily obtain the denoised hand skeleton joint position from the clean representation, which are then used to optimize and animate the pose of the hand Gaussians. The fourth step of our method is to further eliminate potential penetrations in the diffusion model output with our proposed geometry-aware depenetration algorithm. Our method estimates the penetrated fingers and then repose them appropriately on the object surface. The penetration estimation is quite simple. We attach cameras to the hand skeleton joints and set their orientations according to the post-skeleton directions. Then we render depth maps. If the penetration occurs, the corresponding finger's depth map will show a valid value. We then optimize the penetrated hand pose, but only the Euler z-axis rotation to avoid any twisting. So no x or y, only the z direction. The Euler z-axis is optimized in the skeleton hierarchical order. We first flatten the penetrated fingers, so into a zero pose. Then increase the root level of the 5 fingers until they contact with the object. Then followed by the middle level joints and finally the tip level joints. So we compare our method with state-of-the-art hand object rendering and the denoising method. Manuals plus GS produce a large gap between the hand and the object. Manuals plus GNOH and 2D GS plus GNOH penetrate with the mark. In contrast, our method outputs stable grasp pose. Manuals plus GS fails to grasp the bottle. The little finger in the third method involves penetration. The sum of the second method inserted into the object. Our methods show far less penetration and instability. Here are more results of our denoising method. The results show that our method not only effectively reduces hand-object penetration, but also produce more realistic rendering quality. The quantitative experimental results demonstrate that our method reduced hand-object penetration depth by 57.3% and produced the most realistic rendering quality, improving 8.3% in PSNR. Here we show the ablation study. As shown in the figure, the input pose exhibit penetrations. Our joint to Gaussian representation, as denoted as the G2GS, produce cleaner fingers than the input pose, but the penetration of the fingers still remains. With the help of our geometry-aware depenetration, denoted as GDP, our G2GS plus GDP fully eliminates penetrations while preserving the depenetrated hand pose similar to the G2GS results. Using only GDP without our G2GS representation eliminates penetrations, but output a pose less similar to the ground truth pose. The numerical results also validate the above visualization. So in conclusion, we introduced the first 3D Gaussian hand-object interaction rendering denoising framework. The second, we present a novel joint-to-Gaussian surface representation for capturing accurate hand-object relation. And we propose a novel geometry-aware depenetration method. Our method also have several limitations. First, the finger length of the pre-trained hand Gaussians differ from those of the user's physical hand. And the second, reconstructing hand and object Gaussians rely on dense field image data with segmentations. Third, though our method support real-time hand-object interaction rendering, the diffusion and depenetration process takes about 10 seconds in total. So in future work, we will fine-tune the finger length of the hand Gaussians to better fit each user's hand, enabling more accurate post-driving animation. And we will replace the diffusion model with a more efficient generative models and substitute the iterative depenetration method with a closed-form solution to speed up our method. Thanks for everyone's listening.
Questions? No questions. Okay, I may start with a question. So, if can you maybe go back to slide number 2?
Okay. Number 2.
Yeah. It was one of. Yeah, this one, please. Yeah, there was a little video here on the or it said, yeah, perfect. I was a little bit wondering. So, you only. If you want to grab something, right, then you only move the fingers at only the rotations, right? So only on the on the z-axis, right? So the x and y-axis, and you also have that on one of the other slides here, is locked, right?
No. The x, y, and z can be optimized by our diffusion model. And
Yeah.
our second contribution, the depenetration algorithm, only.
Can you speak
further-
in the
Okay.
microphone, please?
So you can see, the first method, the diffusion model will optimize the x, y, and z pose of the hand
Yeah.
to produce initial denoised hand skeleton. But the skeleton could maybe still some penetration. So we propose another geometry-aware depenetration to further estimate and eliminate the penetrations by optimizing the only z over x angles.
Okay, because if you go one slide ahead, like on slide number 9.
Okay.
No, on the 9. One slide.
9?
No,
Okay, 9. Oh, sorry.
9. Yeah, on that
This
axis.
one.
You're here in that set Euler axis, so there is in the image at least, there is the x and y axis locked with that.
The geometry-aware depenetration only optimizes the.
Yeah,
Yeah.
okay. That's my okay, got it. So and then that's why it's like moving like this.
Yes.
Okay, and how is it then? That's my actual question.
Okay.
How is it working if you have more complex objects where it's not like, for example, where you only can grab with 2 fingers or something like that? Would it also work?
I'm sorry.
If you only grab with 2 fingers, like I would hold this like this, and having these fingers not like here, so like that, would it also work?
Okay. This method, we first estimate the penetrated fingers. So
Okay.
if the 3 fingers, they do not contact with the object, we will fix
Okay, got it.
their angles.
Okay, perfect, thanks. Do we now have questions? Okay, if not, then I would say it's over. Thank you again for that very nice presentation.
Thank you.